Okay, go ahead. Okay. Hi everyone, welcome to this week's webinar. So today our speaker is Dhara Thakkar. She is a PhD student working broadly in theoretical CS at IIT Gandhinagar. She works with Professor Cayley. So before that, she got her MPhil and MSc in maths from Sardar Patel University in Gujarat. So she is generally interested in developing efficient algorithms for problems in algebra, and her current work involves designing algorithms for some group theoretic problems. And she also enjoys tackling problems in graph theory, parameterized complexity, and so on, which is evident from some of her latest work. So I also urge the audience to visit her website sometimes, where apart from her research work, you can also find her non-academic blog, which is really fun to read. So without further ado, the floor is all yours, Tara.
Thanks, Varun. Thanks for the kind introduction. So, hi everyone. Today I'll be talking about my recent work, which is a polynomial time algorithm for the minimum generating set problem for groups. And this is a joint work with Piriswar Das and Andrea Lucchini. So, if you have any question at any point of time, please stop me. So I will so in this talk I will follow this order. So first we will see some basic terminologies and how we represent group to an algorithm. Then I will define the problem, and later we will see a polynomial time algorithm. And if time permits, I will also consider these results, which is a quasi-polynomial time algorithm for primitive permutation groups. Okay, so let me start with the definition. So a group G is a finite set together with a binary operation star, and a set G with this binary operation star should satisfy some properties. One, it should have this closure property where for every x and y we want x star y should be in G. Then this associativity property, which is for x, y, and z in G, we want that the associativity between these three elements should hold. And then this identity property, where for every x in G, there should exist some identity element E, such that x star E should be equals to E star x should be equals to x. And later we also want that for every element x of G, there exists some y in G such that x star y equals to y star x equals to identity, and such y is known as inverse of x. So if we have a set G and a binary operation which satisfies this four property, we will call it as a group. Then, for example, if we take this symmetric group on n symbol or a cyclic group of order n, they are an example of a group. Uh, a, an abelian group is a group which has this additional property where for every x, y in G, we want this commutativity should hold. That is, x star y should be equals to y star x. For example, Zn here is an example of a commutative abelian group. Okay. So there is another definition. So given a subset T of G, we call T as a generating set of G if for every element of G, we want that it can be written as a finite product of elements of T or their inverses. So if we have such a subset of G, we call T as a generating set. For example, you might have seen that the group Sn has a generating set of size 2, which is this transposition and n-length cycle. And it also admits another generating set, which is this n-1 transpositions. So it has size n-1. So a group might have different generating set and their sizes might also be different. So that is why we define minimum generating set. A minimum generating set of a group G is a generating set whose cardinality is minimum, and we denote this cardinality by D of G. So, for example, you can see that if we have a symmetric group on n element set, then it has a generating set of size 2, and it cannot have a generating set of size 1. So D of Sn is equals to 2. There are some more definitions. So the group of all permutations on n element set is Sn, and if we take any subgroup of Sn, they are known as permutations group of degree n. So, for example, AN is a permutation group of degree n because it is a subgroup of Sn, but we can take any subgroup instead of AN. So there is this fact in group theory. It says that given a finite group G, it admits a generating set whose size is at most log mod G. We will use this fact in the later slides. So that it says that we can construct a generating set whose size is at most log mod G. Okay, so since we will be talking about algorithms on group theoretic algorithms, so let me tell you how we represent group to an algorithm. So there are certain representation of a group. In this talk, I'll be considering two representation. One is this Cayley table representation where we have given a multiplication table of a group explicitly as an input to the algorithm, and at any point of time we can access b star c in order one time. So this is how we have given its multiplication table, and you can see that here in this representation the input size will be polynomial in the order of g. Now there is this representation known as permutation group representation where we have given a group G as a subgroup of symmetric group, and the group G is represented by a generating set say T. Now this representation is more general. Why? Because we have seen just now that any any group G has a generating set of size at most log mod G, and here since G is a subgroup of Sn, it can have size at most n factorial. But the generating set T, which is representing G, has size at most n log n. So, like here, the group could have n factorial size. It has n factorial size, but the generating set that it represented, it has just size Pauline n log n. This permutation group representation is more space efficient and it is more general than the Cayley table representation. And here the input size is Pauline log mod g comma n. From now on, we will consider this Cayley table representation, and later we will consider this permutation group representation. So we will assume that our group G is given by its multiplication table, and let us define the problem. So a minimum generating set problem is defined as follows. As an input, we have given a group G. Okay.
Am I audible?
Yeah.
So sorry, just a simple clarification. So you have cardinality of G and there's n. So just like small n is just going to be the size of this permutation group.
Yes. So we will represent a permutation by you can say an array of length n.
Okay.
Yeah. So each of the permutation will be represented like that, and the log mod G many permutation can be there. So we have to add n here because the size of the group G can be very small, but still we have an n length permutation. So we need n in the input size. So the problem is defined as follows. We have given a group G by its Cayley table, and the question is that can we find the size of the minimum generating set, or that is we denoted by dg. So can we find a d of g? So that is the question. So we want to find the size of the minimum generating set, that is d of g. But the algorithm that we have designed, it also finds one minimum generating set together with dg. So let us see very brute force idea how to solve this minimum generating set problem. So we have seen that any group can have a generating set of size at most log mod g. So this fact can help us to design an like trivial algorithm. So what we can do, we can collect all possible subsets of G whose size can be at most log mod G, and we can check whether that subset T generates G or not. And for now, assume that given a subset T, there is a polynomial time algorithm that checks whether T generates G or not. So suppose that this second step can be done in polynomial time, then the running time of this trivial algorithm is quasi-polynomial in the size of the G, because we are trying all possible subsets whose size is at most log mod G, and that is size of G choose log mod G. So that is this trivial algorithm. So it runs in quasi-polynomial time in the order of G. Now let us see how can we do this second step in polynomial time. So there is a problem known as membership testing, where we have given a group G and a subset T of G and an element X in G, and we ask whether X is in the group generated by T or not. And it is known that membership is in P. So here we just need to use membership multiple times. What we can do, for every element of G, we can check whether G lies in the group generated by T or not. If we get yes for every element of G, then G is a subgroup of this group generated by T. So this is a generating set. So if we use this membership testing, then we know that
What is the
this trivial algorithm. Sorry.
What is the algorithm for membership testing?
So, for example, let's say you have a Cayley table. We want to do membership testing in Cayley table. So, how you can do? You have elements of T. So, you can construct a Cayley graph. You start from the root element will be the identity element. Then you keep on increasing the graph by adding edges from identity to the elements of T. So identity will have neighbors, uh, number of neighbors which are elements of T. Then each of those neighbors have branches. Again, like from identity, suppose T is just T1, T2. So we will have E, then age T1, T2. Then this age T1, the vertex T1 has another two neighbor, which is T1, T1 and T1, T2. And we will keep on generating this graph till the repetition will start, and then whatever.
This is polynomial size of G, not the log of size of G.
Sorry, this is polynomial in
the size of G.
Yeah. So that is what we want. Here the input is given by Cayley table. So the input size is polynomial in the size of G, right?
Is there an algorithm that is polynomial in the log of size of G for membership or no?
Sorry, I cannot.
Question was if there is an algorithm that runs in time polynomial in the log of size of G.
Okay, so for permutation group representation, there is like to solve membership, you again use an algorithm that is known as order finding. So order finding has a polynomial time algorithm, and so then you can find order of T and order of the group generated by T comma G. So that is how membership in permutation group representation can be done.
Yeah, but it's not an obvious algorithm. Yeah, so it's the Schreier-Sims algorithm. But yeah, but it's, no, the algorithm for membership and permutation groups, I think, is called the Schreier-Sims algorithm. It's just that it's not.
Yeah. So now your claim reduces to finding the order, but the order finding algorithm uses Schreier-Sims algorithm, because now you want to find order of G. To find order of G, you can use orbits and stabilizers, and stabilizer is a subgroup of G. So there you can use Schreier-Sims algorithm to find generators for the subgroup. So ultimately, it uses Schreier-Sims algorithm, but like for membership, it is the order. It reduces to order finding.
This is the idea where you have 2 pointers and you spread it straight.
It's, I mean, it's a little more complicated because the standard way of doing it, what will end up happening is your generating set size will become larger and larger. The key in Schreier-Sims is to somehow prune the generating set size back to.
No, but that is for membership. That's for computing the order.
No, even that. I mean, it's yeah. It's not a, it's a little involved, but it's yeah. Yeah, so Rohan's also saying you need to get something called the.
So, this order finding uses Schreier-Sims algorithm, but I'm not sure if we can use directly shares in the algorithm to find order, to solve membership.
Okay.
Yeah, but throughout in your talk, I guess we are dealing with a Cayley table. So poly NG is perfectly fine.
But later we will later I will I will claim that all the proof or all the like algorithm that we will do.
I think network.
Maybe she's still on the phone.
No, she. I think that's. Can you just text her or something? Can you hear us?
Hello? Yeah. I can hear you.
Yeah, you might have to reshare your screen. Yeah.
Yeah. Yeah, so I was telling that for now I am assuming that all these things given in Cayley table, but this is also true for even permutation group representation. And there also membership testing is in P, so we don't have any problem.
Yeah. Can you just go to full screen mode if that's okay? Okay.
Sorry?
Can you go to the full screen mode?
Oh, sorry. Yeah.
Yeah, thanks. Yeah.
Yeah. So, so I was saying that this algorithm, minimum generating set problem admits quasi-polynomial time algorithm. So there is a certain polynomial time algorithm known for some special classes of group. For example, if we have given a group G which is nilpotent and it is given by its Cayley table, then Arvind and Turan proved that minimum generating set problem can be solved in polynomial time. And in the same paper, they also claim that this problem is in the class D space of log square mod G. But there is this result which says that if we have a group G, which is solvable group, then also minimum generating set problem admits a polynomial time algorithm. And this is proved by Lucchini and Menegazzo in 1994. But in the paper, in their paper, they have presented a practical algorithm. But if we analyze the running time, that is actually a polynomial time. So that is the results that were known before we started working on this problem. So I would like to tell you why I have started working on this problem. But before that, let me give you some definition. So a subgroup is a normal subgroup if G inverse HG should be equals to H for all conjugates H, of H, it should equals to H. Then, for example, this subgroup A5 is normal in S5. Then we say that a normal subgroup H is minimal normal if it does not contain any normal subgroup of G other than H or 1. So that is we call a minimal normal subgroup. And the same example, which is A5, is minimal normal in S5. Then we say that a group G is simple if it has no proper non-trivial normal subgroup. For example, if we take a cyclic group C5 or any cyclic group of order P, then it is a simple, and this alternating group A5 is also simple group. So it is known that every simple group admits a generating set whose size is at most 2. But once we consider its direct product, like product of simple group, the situation becomes more interesting, because it is known that even if we take any larger power till of A5 till 19, then the size of the minimum generating set is just 2. And once you take the 20th power of A5, it is just 3. But more interesting is the following. So if we consider the direct product of A5 and till 64,64040 power, then the size of the minimum generating set is just 5. So it is interesting that can we design an efficient algorithm that's even answer, or that even solves minimum generating set problem for this weird class of group, which is product of simple group. And also there is this problem known as graph isomorphism problem, where we have given two graphs x and y, which is we ask whether x is isomorphic to y or not. Then there is so group isomorphism problem is a special case of graph isomorphism problem, where we ask whether G, given a group G and H by the Cayley table, we ask G is isomorphic to H or not. So this group isomorphism problem admits trivial quasi-polynomial time algorithm, and it is known as generator enumerator algorithm. And this algorithm is very easy to understand. What it does, it first pick a generating set of size L. It picks any generating set of size, say L, of size at most log mod G, and then it try all possible subsets of H of size at most L, and it tries to define an isomorphism between the generating set of G to generating set of H. So it is like we can see that since we are trying all possible subsets of H, the running time is quasi-poly in size of the group G. Now, this is the trivial algorithm is similar to the trivial algorithm of minimum generating set problem. So our initial goal was to find some relation. So it can we study minimum generating set problem and find some reduction or some relation or some uh, efficient algorithm for certain special classes of group isomorphism problem. So that is why we consider this minimum generating set problem. First we consider the class which contains all those group G, and G is a product of simple groups, and we prove that if G is a product of simple group given by the Cayley table, then minimum generating set problem has a polynomial time algorithm. Then we also improved the quasi-polynomial time algorithm for general groups by giving the following results, where we proved that for any general group G given by the Cayley table, we can have an algorithm that solves minimum generating set problem, and it runs in size of G power 1/4 log mod G plus order 110. So these are the results that we have obtained initially, but the following question was still open, whether can we design a polynomial time algorithm that solves minimum generating set problem for all finite group given by the Cayley table.
Can you go back?
Sorry?
Can you go back one slide?
Your voice is not.
Yeah.
Can you go back one slide?
Yeah.
What is P in the base of the logarithm?
Here, P is the class of polynomial time algorithm.
No, you have a G to the 1/4 log PG, right? In the second
Yeah.
theorem.
Oh, sorry. Yeah, that P is the smallest prime that divides the order of G.
Okay.
Yeah. So in the trivial algorithm also we have this log mod G to the base P.
So just want to, so in your first theorem, if the group is not given as a product of simple groups, right? Or is it just given as a Cayley table, or do you also know what the product of simple groups are?
We only have given group G by its Cayley table.
Okay.
How does the first one compare to the algorithm you mentioned in a few slides ago from membership?
Sorry.
So the first theorem, how does this compare to the algorithm about nilpotent groups or solvable groups, etc.? Is there a way?
As compared to the time complexity or the proof?
I mean, is it stronger? Is it incomparable? What is the connection?
So, I don't understand the question explicitly, but we cannot say that our result will answer the nilpotent group result, because this is just product of simple group.
Okay. So in the sense that the previous result is not a corollary of your first theorem.
Yeah. It is not a corollary. So then we obtained a polynomial time algorithm that holds for any finite group, which is given by the Cayley table. So let us see the idea behind this polynomial time algorithm. So there is this result by Geshut. It says that suppose n is a normal subgroup of a group G, and we have the generating set for this quotient group. So if we have some information about a group G, which is like G can be generated by L elements, then this theorem says that you will be able to find U1 to UL from N such that G has a generating set of this kind, G1 U1 to GL UL. So if you notice that this theorem gives us idea to extend the generating set of the quotient group to the generating set of the actual group. And there is another theorem which says that given a finite group G and a minimal normal subgroup N of G, suppose that quotient group has a minimum generating set of size L, then G cannot have generating set. So G has a minimum generating set of size L. It can be D of G can be at most L plus 1 and it can be at least L. So DG can be either L or L plus 1. So these two theorems gives us a better algorithm which is recursive, and it is very easy. So what we can do, we can first find a minimal normal subgroup of G. It is known that there is a polynomial time algorithm that finds a minimal normal subgroup. Then what we can do, we can recursively find a minimum generating set for this quotient group G quotient N. Now suppose that we have this generating set G1 N to GLN for this quotient group, and we want to lift this generating set to a generating set for G. So what we can do, we can first try all possible L tuples U1 to UL from size of n power L set from this mod n power L set, and we can check whether these spatial generating set G1 U1 to GL UL will generate G or not. And from the previous theorem by Geshut, we know that if G has a generating set of size L, then we will be able to find one generating set in this step. Otherwise, we know that G has a generating set of size L plus 1, and we will again use the result of Geshut, and we can try all possible L plus 1 length tuples, and we will check whether they generate G or not. So this is a bit better algorithm, but if we analyze the running time, it takes mod n power L plus one many tuples we need to try, and eta is, let's say eta is the number of iteration. So since it is recursive algorithm and the size of the group is reduces every time, in each step it is reduces, so eta can be at most log mod G, and since n is a subgroup of G, it can be bounded by a size of G. So this runtime is again quasi-polynomial in the size of G. But the algorithm, the idea behind this algorithm is better than the trivial algorithm. So we ask the following question. So can we, instead of trying all possible mod n power L plus 1 tuples, can we find some spatial subsets such that we will take all the tuples from that spatial subset, and we will say whether G can be generated by that subsets or not. So what we can ask, can we reduce the search space? So that is what we have done. Now suppose that in this algorithm, this n, the minimal normal subgroup, is abelian. So then in this case, the answer is already there in the literature. So there is a theorem by Lucchini and Menegazzo which says that if we have a group G and let's say n is the minimal normal subgroup, but n is abelian minimal normal subgroup of G, and suppose that the quotient group is generated by this G1 n to Gn n, then they prove that we can have a generating set for the actual group G. So if DG can be at most L, or I should write equals to L. If DG is equals to L, then either the inverse images of this G1 n to GLL will generate G, or we must have some I and J from this range such that G will be generated by this spatial generating set, which is G1 to Gi minus 1, Giej, and J plus 1 to Gi. Otherwise, we know that Tg is L plus 1, and in this case, it is easy because we can add any arbitrary element which is non-identity from N. And this L plus 1 length subset will generate G. So this theorem handles the case when N is abelian minimal normal subgroup. So if you see that now instead of trying all mod n power L plus 1 tuples, we just need to try these generating sets, and these are at most ml plus 1, and which is bounded by log mod G square. So we can handle abelian case easily. And so the question is that what we can do if the minimal normal subgroup is non-abelian.
So here you are saying even
Yes.
abelian minimal normal subgroup, you don't mean consider all abelian normal subgroups and out of them take the minimal one. Right? You are saying if the minimal subgroup is abelian, then this happens.
Yes, if the minimal normal subgroup is abelian, then we can do this. I didn't get your question. You are asking.
Yeah, that was the, I think you answered.
Right. I thought cement among all abelian normal subgroups take the minimal one.
Yeah, no, I think here it's like if the minimal normal subgroup happens to be abelian.
Yeah.
Yes, yes.
There was an ambiguity.
So I will present the update, like the new algorithm, where we use this theorem only when the minimal normal subgroup is abelian, and that check is done in polynomial time. So if we can handle the case when the minimal normal subgroup is non-abelian, then we are done. So for that, let me introduce some definition again. So a fraternity subgroup of G is a subgroup where it is intersection of all maximal subgroups of G. So we'll consider all maximal subgroup of G and take it intersection. The subgroup we get is a fraternity subgroup. For example, if we take this S3, then it has the maximal subgroup of order 2 and order 3. So, and it doesn't intersect. So the fraternity subgroup is trivial. Also, this is the crucial definition that will be used in handling the non-abelian case. So a finite group L, we call it as a monolithic primitive if L has a unique minimal normal subgroup, and that minimal normal subgroup should not contain in the fraternity subgroup of L. So such group we call it as a monolithic primitive group. For example, if we take S3, then C3 is its unique minimal normal subgroup, and we see that the fraternity subgroup of S3 is identity. So C3 cannot contain in the fraternity subgroup. So S3 is a monolithic primitive group. Now, for a monolithic group L, we can define. So let's say let's take L is a monolithic primitive group and A be its minimal normal subgroup. Then for each positive integer k, we can define crown-based power of L. It is just a subgroup of direct product of Lk, but it is a special subgroup. So it contains all those tuples of length k from direct product of L, such that this condition should hold that each Li should be equal, so L1 should congruent to L2, should congruent to L3, and so on. Lk minus 1 should congruent to Lk modulo A. So we have a monolithic group L, and we define its crown-based power L subscript k. For example, if we take a simple group S, then by definition it does. So S is itself a minimal. It cannot have any minimal normal subgroup other than S. So this A is S itself, and in that case, Lk is Sk. So from now on, we will take delta to be some spatial number, which is at most log mod G. And this is actually defined in terms of N and G, like N is a minimal normal subgroup of a group G. But For this talk, we will just take it is some special number which is at most, it can be at most log mod g. So first, to handle the non-abelian case, we have proved the following theorem. So this is a lemma. So we improved the search space for some special classes of group, which is what this lemma is about. So we have a monolithic primitive group L, and by definition, it has a unique minimal normal subgroup. Suppose it is non-abelian. Now we consider its crown-based power H, which is L delta, and let's take any minimal normal subgroup n bar of H. Now take T to be this special number. It is dependent on delta, which is 13/5 plus log delta to the base mod n. Now, if we know the generating set for this quotient group, H quotient n bar, and also if we know that T is less than or equals to L, then we can find some number, some element from n bar, which is n1 to nt, such that this special subset, which is g1 n1 to gt nt, gt plus 1 gl, this will generate H. So instead of trying mod n power L many possibilities, now we just need to try mod n power T many possibilities, and T is also this special number. So this may help us to design efficient algorithm, but this is only true when the group H is crown based power of some monolithic group. So then we proved following result. This says that, so this theorem claims that we can even reduce the search space for any finite group G. So we have a finite group G and n to be its minimal normal subgroup, which is non-abelian. Suppose we know that the quotient group is generated by G1n to GLn, and we are taking T to be again this special number. Now, if we know that T is at most L, then we can find some n1 to nt in n such that G is generated by this spatial generating set. So we may use, we can use this theorem in the algorithm, but the problem is that we only use this theorem when T is less than or equals to L. So we will overcome this in the next slide, but let us see proof idea, the proof sketch for this theorem. So first, what we have done, we using G and N, we have constructed a monolithic group, say L. So it can be constructed using the information of G and N, but for now assume that we have this monolithic group L. Now, once we have monolithic group L, we can consider its crown based power H, and let's say n bar is minimal normal subgroup. Now for H and n bar, we can use previous lemma and we can have a special generating set for H. Now the question is that how can we lift this generating set to a generating set for G? To handle this, we prove following. So if we have a special generating set for H, then the inverse images in G will also give us gives us a generating set for G. So this says that we can even reduce the search space for any finite group G if T is less than or equals to L. Now let us see how do we handle the case when T is not less than or equals to L. So this is the final theorem that says that if we have a quotient group, if we have a minimal normal subgroup N, which is non-abelian, and if we know that the quotient group is generated by L elements, then we only need to try mod n power T many elements and we can find a generating set for G. So the proof is easy to see. Is there any question?
No.
Okay. So if T is less than or equals to L, then from the previous theorem, we can have a special generating set of G. So here we need to try mod n power T many T tuples, and we can construct one generating set for G. Now, what if T is not less than or equals to L? In this case, we can show that even L plus 1 is also less than or equals to T. This is easy because L is strictly less than T. And we can show that DG cannot be L, so it has to have L plus 1. Now, this is what we have shown, that DG has to have L plus 1, and since L plus 1 is less than or equals to T, now we can use Gaussian results that I have stated initially. And what we can do, we can try all possible subset of this form, which is G1 N1 to GL NL NL plus 1, and check whether one of them generates G or not. And since DG equals to L plus 1, Gaussian's lemma guarantee that one of these possible subset should generate G. So that is how we can even handle the case when T is not less than or equals to L. Now, let us see how this theorem gives us the algorithm, which is polynomial time. So the improved algorithm is as follows. So the step 1 is as it is, where we find a minimal normal subgroup N. Now we first check whether suppose that recursively we have a generating set for this quotient group, which is G1 N2 GLN. Now in step 3, we first check whether N is abelian or not. If N is abelian, then we know that either we can handle this abelian case easily, because either G1 to GL will generate G, or we will be able to find some INJ such that this spatial generating set will generate G in case when G is generated by L elements. If not, then we know that G will be generated by L plus 1 elements, and we can add arbitrary element from N, which is non-identity. So the crucial part is how do we do non-abelian case. So if N is non-abelian, then we first check whether the T that we have defined is at most L or not. We have L recursively, which is the size of the generating set for the quotient group. So we can first check whether T is less than or equals to L. If yes, then the theorem that we have proved guarantee that we will be able to find one generating set of this form, which is G1 U1 GT UT GT plus 1 GL. So we will try all possible mod and power T tuples, and we will check whether this generating set will generate G or not. If not, if yes, then we will return. Otherwise, we know that G will be generated by L plus 1 element, and we will check all these tuple, which is of the form G1 U1 GL UL and UL plus 1. Now we will check whether some of these tuple generate G or not. And since G has a generating set of size L plus 1, we have a guarantee from Gaussian lemma that one of these tuple should generate G. So this is an improved algorithm. Now let us analyze the running time. So the only crucial step is the non-abelian case, because abelian case is easy to see that it can be done in polynomial time, and we can also find minimal normal subgroup in polynomial time. And in the non-abelian case, either we need to try mod n power t possibilities, mod n power t many tuples in the first step. If we fails in the first step, then we will go for the next step, and there we are trying mod n power L plus 1 tuples. And for each such tuple, we are spending polynomial time to check whether they generate G or not. So this is so T is the spatial number that we have taken, this spatial number, and we have already shown that L plus 1 will be also bounded by T. So that is the running time is this, and it is easy to see that this is polynomial in the size of the group. So if you take, so I have not defined what is the number delta is actually, because to define delta, I have to introduce 3 or 4 definitions. So for us, it is okay if we take delta to be equals to log mod G. But if we take the explicit definition of delta, we can reduce the constant to 4 or 5. It cannot be more than 5. So that is the polynomial time algorithm for minimum generating set problem, and we have the following result, where we say that if we have a group G of order m given by its scalar table, then there is a polynomial time algorithm that finds the minimum generating set of G.
Dhara,
So-
in the
Yes.
previous slide. No, just something simple. So in each of these cases, so so we end up with some generating set for our group, and then what was the theorem which told us that this would in fact be the minimum generating set?
So from the like the algorithm, from the algorithm only we are constructing a minimum one, right? Whatever theorem that we have proved. So whenever we are lifting a generating set from the quotient group to the actual group, we want that it should lift as a minimum generating set.
So when you look at this minimum normal subgroup, you take its minimum generating set, then I guess one of the theorems said that once you do this lifting, then what you end up with is also a minimum generating set for the original
Yes, yes.
Oh.
So we take a minimal normal subgroup, we take the quotient by it, and the quotient like recursively we assume that we have a minimum generating set for the quotient group, and the like the step that we can also lift this generating set of the quotient to a minimum generating set for the group.
Okay.
Yeah. So that is the polynomial time algorithm result. Later we consider this permutation group representation that we have already seen. Here the group is given by its generating set. So first we have this result that the polynomial time algorithm that we have seen just now, it is also true even if we have a group G given by its given by its permutation group representation. But what is the so here the algorithm, so the running time of the algorithm is size of the group, a polynomial in the size of the group, where in this representation the input size is polynomial in the log mod G. So this theorem is even still better than the brute force algorithm, which is quasi-poly, but it is not efficient in terms of the size of the input. But the algorithm still works in this representation as well. Later, I plan to present another result which is on permutation group representation. So I think let me just give you an overview of the result because there are certain definitions that I have to introduce, and I think I don't have that much time. So we consider a primitive permutations group. These are groups which has certain properties. So it has been defined in terms of transitive groups. If or you can assume that primitive permutations groups are groups which has all its stabilizers are maximal normals, maximal subgroups. So we consider a group G, we find all its stabilizers. If those are maximal subgroups, then we say that G is primitive group. Now, when people started working on permutation group representation problem, their first so they first handle the case when the group is primitive permutation group, and that is why we also consider the group which is primitive, and we show that if the group is given by its generating set and it is primitive permutation group, then d of G can be computed in quasi-polynomial time in the degree of G. So here n is the degree and the running time is quasi-poly in the degree of G and not the order of group. But here we are just finding d of G and we are not finding a generating set. So the proof idea is as follows. We first so I will briefly discuss the proof idea. So we have this is known that this such primitive permutation group has a generate d of G is bounded by some function of log n. So we use this bound, but the problem is that the size of the group could be very large. So if the size of the group is also quasi-polynomially bounded, then we can do brute force that we have already seen. But what can we do if the size of the group is very large? That is, it is not bounded by a quasi-polynomial time function. So in that case, we show that G has a G has a special minimal normal subgroup, which is known as SOCL, which I have not defined. But G has a special minimal normal subgroup such that the quotient group has a small size. By small, I mean quasi-polynomial size. And so we can use brute force algorithm for this quotient group. Now, then we can then there is a result that says that d of G will be equals to d of the quotient group when the quotient is taken when for this special minimal normal subgroup, which is SOCL of a group G. So that is how this quasi-polynomial time algorithm result. This is how we proved quasi-polynomial time algorithm to find DG for primitive permutation group. So to conclude the talk, we have seen a polynomial time algorithm for the minimum generating set problem when the group is given by Cayley table or even in permutation group representation. And we have also seen this primitive permutation group where we find d value of G for primitive permutation group in quasi-polynomial time. Thank you. Any question?
Any questions, anyone?
So I have a couple of questions. So is it even easy to see that if like for example, if someone, I'm talking about the permutation group setting.
Hmm.
There, if someone gives you a purported minimal generating set, can you even check if it is the smallest generating set? I mean,
Sorry, someone gives me a minimal generating set.
gives you a subset of generators
Hmm.
and claims that this is a minimal generating set for your group. Is that even verifiable quickly? I mean, do we know?
Minimal we can verify easily, but minimum we cannot. Minimal we can easily verify.
No, we do not know. Okay. And okay. Or in general, even it's like it's not even clear that is there a generating set for your group of size at that is trivially in NP. Is it?
So
Sorry.
that is what we have answered. So suppose if you have given a group G and an integer k, and you want to know whether G has a generating set of size k or not, you can find its minimum generating set like d value of G, and if you just need to check whether k is larger than d of G or not. If k is larger than d of G,
Polynomial in the size of G. I mean, I was thinking about it in the permutation group setting again.
okay.
So in
In
that
permutation group setting, like I am not sure whether there is an algorithm which is better than the polynomial in the size of the group.
so are there any lower bounds for this? I mean, like, is there reason to believe that poly in G is the best we can do in the permutation group setting?
No, I am not sure about it. I don't think there is any lower bound.
Okay.
So I had a question, which is, so there's one statement which said that there is also there's a deep space log square in algorithm or something, right?
Yeah.
That was for this problem. I think that was also for this finding the
No,
minimum.
this is for this problem, but there they have assumed that the group is given by Cayley table.
Oh, there the group is.
Hmm.
Okay. No, then I was thinking, so the algorithm that we have right now, it's a polyspace algorithm, is it?
Sorry.
The current algorithm that you have given us, which is given the K table, we can in polynomial time find the minimum generating set. So what is the space usage there?
I think it is poly in log mod G only.
Oh, it is poly in log mod G.
Yeah. So their results about this space complexity that is still better.
Taking in some reason.
And this result which says that the min gen is in D space log square mod G. So they basically use the idea of this trivial quasi-polynomial time algorithm, and they show that it is actually in d-space log square mod G.
Right. Any others? Okay. If not, let's thank Dhara again.
Thank you. So may I leave the meeting?
Yes.
Sure. Thanks a lot, Dhara.
Yeah, thank you so much. Bye.